This video covers Part 3 of Section 3.10 Epsilon Delta Proofs. We now introduce the formal definition of the limit of a function. Intuitively, we say that the limit of a function f of x as x approaches a point c equals L, provided that, as x gets closer and closer to c, the function values f of x get closer and closer to L. The problem with this statement arises in determining exactly what do we mean by phrases such as approaches or closer and closer. These terms serve to provide an intuitive feel for what the limit of a function is, but are not precise enough to enable us to prove results about limits. The formal definition, developed by Cauchy in the 1820s, which was over 100 years after Newton and Leibniz, provides us with a precise notion of a limit. So here's the definition. Let I be an interval, and let f from I to R be a function. Let C be a point in the domain I, and let L be a real number. Then L is a limit of f at C, which is denoted by the usual notation, the limit as x approaches C of f of x equals L, provided that, for each real number epsilon greater than 0, there exists a real number delta greater than 0 such that, for all x in I, if 0 is less than the absolute value of x minus c is less than delta, then f of x minus L absolute value is less than epsilon. This condition has symbolic form. For all epsilon greater than 0, there exists a delta greater than 0 such that for all x in I, 0 less than absolute x minus c is less than delta, implies the absolute value of f of x minus L is less than epsilon. To get an understanding of this definition, note that the quantity x minus c absolute value appearing in the hypothesis of the conditional represents the distance between x and c. The inequality in the hypothesis, 0 less than the absolute value of x minus c less than delta, has two parts. The right inequality, absolute value of x minus c less than delta, is then equivalent to saying x is within delta distance of c, or x is between c minus delta and c plus delta. The left inequality, 0 less than absolute value of x minus c, is equivalent to saying x is not equal to c. We include this requirement because the value of the function at x equals c is irrelevant to the limit of the function as x approaches c. In fact, the function need not even be defined at x equals c for the limit to make sense and to exist. The quantity absolute value of f of x minus L appearing in the conclusion represents the distance between f of x and L. The inequality in the conclusion, absolute value of f of x minus L is less than epsilon, is equivalent to saying f of x is within epsilon distance of L. The conditional, 0 less than absolute x minus c less than delta, implies the absolute value of f of x minus L is less than epsilon, then means that if x is within delta distance of c, but not equal to c, then f of x is within epsilon distance of L. The definition says that for any positive real number epsilon, there exists a positive real number delta, such that for all x in I, 0 is less than x minus c absolute value is less than delta, implies the absolute value of f of x minus L is less than epsilon. Since there must exist such a delta for any epsilon greater than 0, no matter how small, this means that the function values are getting closer and closer to L as x approaches c. To visualize the definition, suppose we have the graph of the function y equal f of x. As shown in the diagram, as x gets closer and closer to c, f of x gets closer and closer to L. For the graph shown, the function is not defined at x equals c, which is illustrated by the open circle at the point CL. To prove the limit as x approaches c of f of x equals L, we start with an arbitrary epsilon greater than 0. We want the function values to be within epsilon distance of L, that is, between L minus epsilon and L plus epsilon. So between the two horizontal lines shown in the diagram, we need to find a delta greater than 0 such that when x is between c minus delta and c plus delta, then f of x is between L minus epsilon and L plus epsilon. So we want our x to be between the two vertical lines at c minus delta and c plus delta shown in the diagram. For an example, let's let f from r to r be defined by f of x equals 2x plus 3 for each x in r. The graph of f is a straight line. As x approaches 1, we can see that f of x approaches L equal 5. So intuitively, we expect the limit as x approaches 1 of f of x to be equal to 5. Let's let epsilon be 1/2. We want to find a delta such that for all x in r, whenever x is within delta distance of 1, then f of x is within epsilon distance of our limit L equal 5. So we want f of x to be between 5 minus 1/2, which is 4.5, and 5 plus 1/2, which is 5.5. So in the diagram, we want f of x to be between the two horizontal lines. We can determine the limits on x by solving the two equations f of x equals 4.5 and f of x equals 5.5. These have solutions x equals 0.75 and x equal 1.25. We should then choose delta to be 0.25. Delta is going to be the distance between 1 and each of our two limits, 0.75 and 1.25. Now for this particular function, the graph is relatively simple. It's just a straight line, and so we can go through this procedure to solve for delta. In general, it might be too difficult to determine what our delta is, and it may be impossible depending upon our function. So now we want to look at proving the limit of a function. So given a function f of x and real numbers c and L, to prove that the limit as x approaches c of f of x equals L, we need to prove the statement in the definition. For all epsilon greater than 0, there exists a delta greater than 0, such that for all x in I, 0 is less than the absolute value of x minus c is less than delta, implies the absolute value of f of x minus L is less than epsilon. Here are the steps involved in the proof. Since the statement starts with a universal quantifier, we start with a proof by arbitrary element. So we'll suppose epsilon greater than 0 is an arbitrary positive real number. We next need to prove the existence of a positive number delta with the property that for all x in I, 0 is less than x minus c absolute value is less than delta, implies f of x minus L in absolute value is less than epsilon. As in any constructive existence proof, there are two parts to this proof. First, we need to find a real number delta, and we usually need to use the condition f of x minus L absolute value is less than epsilon, which appears in the conclusion, to determine what we should choose for delta. We usually work backwards from the conclusion f of x minus L is less than epsilon to determine an inequality of the form in the hypothesis x minus c is less than delta. We often have to make some preliminary assumptions about x in order to simplify the calculations in this process. The number delta will, in general, depend upon epsilon. However, since the quantifier for delta comes before the quantifier for x in the statement being proved, then the same delta must be used for all x, so delta cannot depend upon x. Second, we have to verify that our choice for delta satisfies our two properties. The domain, delta must be greater than 0. And the domain requirement usually follows pretty easily from the choice of delta. And our propositional function, which is for all x in I, 0 less than x minus c in absolute value is less than delta, implies f of x minus L in absolute value is less than epsilon. This is another universal statement, so to show this, we use a proof by arbitrary element, usually combined with a direct proof of the conditional propositional function. So we'll suppose x is an arbitrary element of the domain I. We'll suppose the hypothesis, 0 less than x minus c in absolute value is less than delta. And we then need to show that this implies the conclusion, f of x minus L in absolute value is less than epsilon. So for an example, let's look at our function f from r to r defined by f of x equals 2x plus 3 for each x in r. So this is the linear function in the previous example. And we want to actually prove that the limit as x approaches 1 of f of x is equal to 5. So we need to show the symbolic form of our statement. For all epsilon greater than 0, there exists a delta greater than 0. For all x in r, 0 less than x minus 1 is less than delta, implies f of x minus 5 in absolute value is less than epsilon. So our c value is the point at which we're taking the limit, which is 1, and our limit L is equal to 5. So we substitute each of those in the symbolic form that we're proving. So we're ready to start our proof. So we'll suppose epsilon greater than 0 is arbitrary, and we need to show that there exists a delta greater than 0 such that our condition holds for all x in r, 0 less than x minus 1 in absolute value is less than delta, implies f of x minus 5 in absolute value is less than epsilon. So we're proving an existential statement, so we'll go ahead and set up our two columns. We need to find a delta, and then we need to verify that delta satisfies the domain and propositional function conditions. So to find a delta, first note for all x in r, the absolute value of f of x minus 5 is 2x plus 3, that's the formula for the function, minus 5. And this equals the absolute value of 2x minus 2. And we can factor 2 out of that, and we'll obtain 2 times the absolute value of x minus 1. Now we want f of x minus 5 to be less than epsilon. So f of x minus 5 in absolute value is 2 times the absolute value of x minus 1, and this is less than epsilon, if and only if the absolute value of x minus 1 is less than 1/2 epsilon. So just dividing both sides of the inequality by 2. Now this last inequality has the form of the inequality x minus 1 less than delta in the hypothesis, with delta replaced by 1/2 epsilon. So this suggests that we should choose delta to be 1/2 epsilon. So now we've found our delta, and we'll go over to the right column and verify that delta satisfies the two conditions. So first we have the domain, and we can say that since epsilon is greater than 0, then delta equal 1/2 epsilon is also greater than 0. So delta satisfies the domain condition. And for the propositional function, we'll suppose x in r is arbitrary, and we'll suppose the hypothesis 0 less than absolute x minus 1 less than delta, and we need to show the absolute value of f of x minus 5 is less than epsilon. Now from the work on the left, we know that the absolute value of f of x minus 5 is equal to 2 times the absolute value of x minus 1. So the absolute value f of x minus 5 is going to be less than 2 delta, since the absolute value of x minus 1 is less than delta. And delta was 1/2 epsilon, so this equals 2 times 1/2 epsilon, which simplifies to epsilon. So this proves our conclusion. So this proves the propositional function. Now we've found our delta, so this proves the existential statement, and so we can conclude that the limit as x approaches 1 of f of x is equal to 5. Now let's examine how this proof was done. For the proof, we need to find a delta that satisfies the propositional function in the definition. So we started by evaluating absolute value of f of x minus 5, which appears in the conclusion of the conditional in the propositional function. For the conclusion, we need the absolute value of f of x minus 5 less than epsilon. And so since absolute value f of x minus 5 is 2 times the absolute value of x minus 1, then this holds if and only if the absolute value of x minus 1 is less than 1/2 epsilon, which looks like the hypothesis with delta replaced by 1/2 epsilon. And this tells us what we should choose for delta. We can follow a similar procedure in general for these types of proofs. Our goal is to transform the inequality we need in the conclusion to look like the inequality in the hypothesis. We can then read off what we should choose for delta. Depending upon the form of the function, we may need to make some preliminary assumptions in order to carry out this procedure. Now, obviously there are differences, but you'll notice that this is the same general procedure that was used to prove the limit of a sequence. So for another example, slightly more complicated, let's let f from r to r be defined by f of x equals 4x minus x squared for each x in r. So we have a quadratic function. And we want to prove that the limit as x approaches 1 of f of x equals 3. To prove this, we need to show for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in R, 0 less than the absolute value of x minus 1 is less than delta, implies the absolute value of f of x minus 3 is less than epsilon. So we'll suppose epsilon greater than 0 is arbitrary, and we need to show there exists a delta greater than 0 such that the condition is satisfied. So now the calculations to determine delta in this example are a little bit more involved. So instead of writing this using the two-column format, we'll write it each part separately. So we need to first find a delta. For all x in R, absolute value of f of x minus 3 is equal to 4x minus x squared, that's the formula for the function, minus 3. And this is minus x squared plus 4x minus 3 absolute value. And we're going to want to factor this quadratic, so we'll start by factoring out a minus 1. So we'll obtain the absolute value of minus the quantity x squared minus 4x plus 3. And now that factors. So we'll obtain absolute value of minus x minus 3 times x minus 1. And now we can take the absolute value of the product will be the product of the absolute values. And we can drop the minus sign since we're taking the absolute value. And so this is just going to be the absolute value of x minus 3 times the absolute value of x minus 1. Now before continuing further in this proof, let's examine how this proof differs from that in the previous example. In the previous example, at this point in the proof, we obtained the absolute value of f of x minus 5 is equal to 2 times the absolute value of x minus 1. We then said the absolute value of f of x minus 5 is less than epsilon if and only if the absolute value of x minus 1 is less than 1/2 epsilon. And since the inequality absolute value x minus 1 is less than 1/2 epsilon, so there's a typo in the video, it should be 1/2 epsilon, looks like the inequality absolute value of x minus 1 less than delta in the hypothesis, this tells us to choose delta equal to 1/2 epsilon. In this example, we have the absolute value of f of x minus 3 is equal to the absolute value of x minus 3 times the absolute value of x minus 1. Instead of a constant in front of the absolute value of x minus 1, we have the absolute value of x minus 3, which is a function of x. Now, if we had a constant, say c, instead of the absolute value of x minus 3, we could carry out a similar procedure. We would have the absolute value of f of x minus 3 equal to c times the absolute value of x minus 1 less than epsilon, if and only if the absolute value of x minus 1 less than epsilon over c. We could then choose delta to be epsilon over c. So what we want to do is to replace the absolute value of x minus 3 with a constant c. Now obviously, absolute value of x minus 3 is not equal to a constant, so we cannot simply substitute a constant for it. What we can do instead is to make a preliminary estimate for delta and use this to obtain an inequality of the form absolute value of x minus 3 less than c. So now we'll return to the proof to show how this is done. So we're back to finding our delta, and we have the absolute value of f of x minus 3 equal to the absolute value of x minus 3 times the absolute value of x minus 1. Let's assume that the delta is less than or equal to 1/2. Now the choice of 1/2 here is somewhat arbitrary. We could use pretty much any positive number. The subsequent calculations will be different, but still valid if we use a different number. Then the absolute value of x minus 1 less than delta, which is less than or equal to 1/2, implies minus 1/2 less than x minus 1 less than 1/2. So we can rewrite our absolute value inequality as a double inequality. Now, what I want to do is get an inequality for the absolute value of x minus 3. So I'm going to subtract 2 from all three sides of this double inequality to obtain x minus 3 in the center. So we'll obtain minus 2 minus a half is less than x minus 3 is less than minus 2 plus a half. And that simplifies to minus 5 halves less than x minus 3 less than minus 3 halves. And now, since x minus 3 is greater than minus 5 halves and less than minus 3 halves, the absolute value of x minus 3 has to be less than 5 halves. Now, you can think of the absolute value of x minus 3 as the distance of x minus 3 from 0 on the number line. And so the double inequality tells us that the furthest x minus 3 can be from 0 on the number line is 5 halves. So the absolute value of x minus 3 will be less than 5 halves. Now, since the absolute value of x minus 3 is less than 5 halves, then the absolute value of f of x minus 3, which is the absolute value of x minus 3 times the absolute value of x minus 1, will be less than 5 halves times the absolute value of x minus 1. This will be less than epsilon if the absolute value of x minus 1 is less than 2/5 epsilon. And now this has the form, the absolute value of x minus 1 less than delta, with 2/5 epsilon in place of delta. Since we earlier had assumed delta is less than or equal to 1/2, we should choose delta to be the minimum of the two numbers, 1/2 and 2/5 epsilon, to ensure that both conditions are satisfied. That is, we want to choose delta to be the min of 1/2 and 2/5 epsilon, where min means delta equals whichever of the two numbers is smaller. Since delta is the smaller of these two numbers, then delta is less than or equal to 1/2 and also less than or equal to 2/5 epsilon. We now have our delta and are ready to verify that it satisfies the domain and propositional function. So for the domain, we need to show that delta is greater than 0. Well, since epsilon is greater than 0, then that should be a 2/5 epsilon is greater than 0. And since 1/2 is also greater than 0, then delta, which is the min of 1/2 and 2/5 epsilon, will be greater than 0. And next we need to verify the propositional function. So we'll suppose x and r is arbitrary. Suppose the hypothesis, 0 less than absolute value of x minus 1 less than delta. Since delta is less than or equal to 1/2, then this implies absolute value of x minus 1 is less than 1/2, which implies, as shown above, that the absolute value of x minus 3 is less than 5 halves. Then the absolute value of f of x minus 3, which is absolute value x minus 3 times the absolute value of x minus 1, will be less than 5 halves times the absolute value of x minus 1, which is less than 5 halves delta, since the absolute value of x minus 1 is less than delta, which is less than or equal to 5 halves times 2/5 epsilon. That's because delta is less than or equal to 2/5 epsilon. And the 2/5 and 5 halves cancel, leaving us epsilon. So this proves the conclusion of our propositional function. So this proves the propositional function, and this proves the existential statement, and thus the limit as x approaches 1 of f of x is equal to 3. Okay, for one final example, let's look at this function in the previous example once again. So f from r to r is defined by f of x equals 4x minus x squared for each x in r. And from the previous example, we want to find the value of delta corresponding to epsilon equal to 0.5, so for a specific value for epsilon. And then we want to graph the function and use the graph to illustrate the significance of delta and to describe the meaning of the definition of the limit. So from the previous example, we chose delta to be the min of 1/2 and 2/5 epsilon. So for epsilon equal to 0.5, delta will be the min of 1/2 and then 2/5 times 0.5, which is 0.2. So delta is the min of 0.5 and 0.2. And obviously the smaller of those two numbers is 0.2, so that's our value for delta. Now what this means is, for all x, if x is within delta equals 0.2 units of 1, then f of x should be within epsilon equals 0.5 units of L equal 3. Geometrically, this tells us that if x is in the interval from 1 minus delta to 1 plus delta, which is 1 minus 0.2 to 1 plus 0.2, or 0.8 to 1.2, then the graph of f should lie between the two horizontal lines y equal 3 minus epsilon, which will be 2.5, and y equal 3 plus epsilon, which is 3.5. And this is indeed the case, as we can see from the graph, which is shown here. So the graph of the function is a parabola which opens down, and we're looking at the limit as x approaches 1 of our function, which is equal to 3, and so that corresponds to the point at 1, 3 on the graph. And so we want our function to be between 3 minus epsilon, which is 2.5, and 3 plus epsilon, which is 3.5. So that means we want the graph to lie between the two horizontal lines that are shown at 2.5 and 3.5. And so we chose delta to be 0.2. And so on the x-axis, we have 1 minus delta is located at 0.8, and 1 plus delta is located at 1.2. And you can see that if x is between those two values, 0.8 and 1.2, then our graph does indeed lie between the two horizontal lines at 2.5 and 3.5. And this is basically what the definition of the limit is telling us. This is for a specific epsilon, and the definition of the limit is for an arbitrary epsilon, or for all epsilon greater than 0. You can find such a delta. Okay, so this concludes the video, and so this is the last video for the course.